class. Today we're going to be doing section 5.19 in AP Stats, which is hypothesis testing for proportions. This is the first time we're talking about hypothesis testing. We have done confidence intervals, and I'll talk about those a little bit today just to reference back, but today is all hypothesis tests. All right, so the first example, a cell phone manufacturer would like to reduce the number of defective batteries produced at their factory to below the industry defect rate of 20%. A quality control engineer institutes changes in the manufacturing process, and the first 400 cell phone batteries produced under the new procedure had a 17% defect rate. Should management of the plant declare a victory? Has their battery defect rate dropped below the industry rate, or is the result simply due to luck or chance? So this demonstrates the need to do a 1 proportion Z test. So it's a proportion because we're looking at the proportion of batteries that have defects. So it's a proportion. 1 proportion because we're just looking at, well, 1 proportion. We've got 400 cell phone batteries. Defect rate is 17%. We're comparing that to the industry defect rate. We always use Z's for proportions. When we get into means, depending on the criteria or information we have, we may use Z's or T's for our mean tests, but for proportions, it's always Z's. So 1 proportion Z test. While the proportion or the purpose of a 1 proportion confidence Z interval is to estimate the population proportion P, so we did confidence intervals before, a hypothesis test enables us to determine if a claim about a population proportion is reasonable or not. It's not going to tell us if the claim is true or false because we're basing all of our math off of 1 sample. So we can't really say that they're right or wrong, true or false based on our 1 sample, but we can say whether our sample provides evidence to support or refute their claims. So hypothesis testing, kind of like confidence intervals, it's very procedural. So there's certain steps that we need to follow. Definitely write all these things down, and you'll do enough of these that you'll probably learn all these steps. It's not like you have to sit there and memorize it, but you definitely are going to need to learn all these. So first, hypothesis tests follow a structured format. There are 4 distinct sections of the hypothesis test. The first one, we have to state the population parameter of interest in terms of P. So we have to define P. Next, we have to state the null hypothesis, which is H sub 0, which is always an equation. And now it says always an equation, but really what this is, it always includes the equality. And I'll explain that a little bit. Technically, you can use an inequality to write your null hypothesis, but usually we just use the equal sign. And if you use an inequality, it has to include the equal. So it has to be like less than or equal to, or greater than or equal to. All right, and then we're going to state the alternate hypothesis, which is H sub A, which is always an equality, never includes the equality. All right, and then note the null and alternative hypotheses must capture all possible outcomes. So that's our hypothesis piece. So define P, write your hypothesis statements. The second one, we need to name the test. In this case, today we're going to be doing 1 proportion Z tests, and we have to check the conditions required for the test. So our 3 conditions we have for these, we have randomization, and these are all the same conditions that we've seen before. We have independence, and we have that the sample size is large enough to assume the sampling distribution of p-hat is approximately normal. So this should be really familiar to you at this point. Next, we get to do the mechanics or the math of it. So determine the test statistic. In this case, it's going to be a z-score value by plugging in our p-hat, our mu sub p-hat, and sigma sub p-hat. Determine the p-value and compare it to the significance level, which oops, that doesn't even look like the word level. We use an alpha, so the Greek letter alpha, to denote significance level. And sometimes the problem will tell you what significance level to use. If it doesn't, one of the ones I usually use is an alpha level of 0.05, so 5% significance level. The p-value is the probability of observing the obtained sample results or an even more extreme value if the null model is correct. By the way, if they want you to interpret the p-value, so we're not talking about, hold on, oops, interpret. We're not talking about using the p-value to write our conclusion. We're going to do that a lot today. But if the problem specifically says interpret the p-value, then this is what you're going to say. This is kind of like your script. So the p-value is the probability of observing the obtained sample results or an even more extreme value if the null hypothesis or the null model is correct. And of course, you would put a bunch of context in there. Now, we are going to reject the null hypothesis if our p-value, which is our probability, is less than or equal to alpha. And this would mean that our sample result is statistically significant. We've learned that term before when we were doing experiments. All right, and then fail to reject H naught or the null hypothesis if the p-value is greater than alpha, which would be a not significant result. And then we would state our conclusion in context, so it has to be in context based on the question being asked. All right, let's look at an example. So if you're in my class, the next page of these notes, I'm going to let you work on those. It's just reading and practicing creating the hypothesis statements themselves. I'm going to jump to doing a full hypothesis test. So I would suggest jumping with me and then at the end kind of going back and practicing those problems that I skipped here. You can always check it with our calendar from our course. All right, so using the opening example, determine if the rate drop in battery defects can be reasonably explained by the new manufacturing process, or is it a result due to chance? Use a 5% or 0.05 significance level. All right, so the first thing we need to do is we need to define our population parameter P. So this is the true proportion, or you can write population proportion. Proportion of defective, batteries. All right, and then our null and our alternative hypotheses are always in terms of P. So always in terms of P, not P hat. So the claim, so if we think about the claim, we go all the way back to the first page here. Their claim was that they wanted to reduce the number of defective batteries produced to below the industry defect rate. So they wanted to see if they had reduced it to below the defect rate from the industry. So that is, if you think about that, does it include 20%? If their defect rate that we found was 20% exactly, would they say that their new manufacturing process is better? It doesn't sound like it. It sounds like it's only going to be better if it drops below 20%, which means it doesn't include the equality. So I'm going to, here we go. So I'm just going to make a little note to myself, and this isn't really part of the problem. It's just part of our thought process. So their claim is that their new P is less than 20%. So their proportion of defective batteries is less than 20% is their claim. Because that doesn't include an equals 20%, it's going to go in the alternate hypothesis. P is less than 0.20. Now this supports claim of defect rate below industry rate. And then the opposite of that would be P is greater than or equal to. Now, a lot of the time we just see equals to, but really its P is greater than or equal to 0.20 because it has to take, so the H naught and the HA, so the null and alternative hypothesis, have to cover all outcomes. So if our alternative hypothesis is less than 20%, then our null has to be greater than or equal to 20%. But a lot of the time, most of the time that you see the null, it's written as just an equal sign, but it's actually greater than or equal to. So it's kind of tricky. You can write greater than or equal to, but it's better to just write equals. And when you see a problem that already has the hypothesis statements written, it's almost always just an equal sign, but it doesn't mean that it's only equals. It's the opposite direction of the alternative hypothesis as well. So this does not support claim. Now, you don't have to write these little things in parentheses that I have here, but it's kind of nice when we get back to the bottom of this and we're making our conclusion to really be able to remember which one of these supported the claim. It won't always be the alternative hypothesis. Sometimes the null hypothesis supports the claim. So it just depends on what the claim is and whether it included inequality or not. That's what tells you if it goes in the null hypothesis or the alternate hypothesis. All right, let's look at the conditions. So first, I named the test, 1 prop Z test. It has to be somewhere in there. So I like to write it right next to conditions. It is reasonable to assume that the first 400 batteries are a good representation of all batteries. So remember, this is our randomness condition. They didn't tell us that it was the randomly selected 400 batteries, unfortunately. They just said it was the first 400. So we're just going to have to assume that they were a good representation of all the batteries and that it was a non-biased sample. Next, we have our independence. So it is reasonable to assume that 400 is less than 10% of all batteries. So independence can be assumed using our 10% rule. The next one, we have to check that the sample size is large enough for a normal distribution. So 400, our p-value, so our n times p is 0.2. That equals 80, which is at least 10, check. And n times 1 minus p, so 400 times 0.8 is 320, which is definitely less or greater than or equal to 10. So sample size is large enough to assume the sampling distribution of p hat is approximately normal. Hopefully you have that kind of memorized. Should be second nature to you by now after doing all of our confidence intervals. All right, so next we get to do the mechanics. So we're going to draw, we have a normal distribution, so I'm going to draw my normal curve, I'm going to label it, I'm going to find my z-score, my probability. So let's see, we have 20%, 0.20, and then if you remember, and I know it's been a while, p hat was 0.17. So if I go back to the first page here, it said that our 400 cell phone batteries produced had a 17% defect rate. So this was p hat from our sample. So we have a p hat of 0.17. So that's down here, 0.17. All right. And then I want to know what's the probability if 0.20 was the actual rate. So if the null hypothesis is true, p equals 0.20. What's the probability I'm going to get my sample result of 0.17 or 17% or more extreme? More extreme means away from that value. So I'm going to go this direction. So calculating my z-score, I have 0.17 minus 0.20 divided by my standard deviation, which is the square root of p, 0.20 times 1 minus p, 0.80, divided by n, which is 400. So remember, these formulas are we've already gone over them. I get a z-score of negative 1.5. All right, and then, whoops, I forgot to grab my z-table. So give me a second here. Wow, it's all the way over here. Whoops, sorry about that, everybody. Okay, so we have our z-table. and we find negative 1.5. We're going less than. So on your Z table, negative 1.50 gives me 0.0668. So the probability that our P hat is less than 0.17, or we could write the probability that Z is less than negative 1.5 equals 0.0, what was it? Negative 1.5668. All right, now that's our p-value. So our p-value was 0.0668. At some point, we have alpha. We want to write it down. Alpha is 0.05. They told us to use an alpha level of 0.05. If they didn't tell us what to use, we would write assume alpha is 0.05. All right, so since our p-value is greater than alpha, so look at your p-value, 0.0668, and compare it to 0.05, that is greater than alpha. If it's greater than alpha, then we fail to reject H naught. So on our previous page, I told you when to reject and when not to reject down here. These ones right there. Reject H naught if our p-value is less than or equal to alpha. Fail to reject if it's greater than alpha. So we fail to reject H naught, which means we're not rejecting H naught. So if I think about what that means, if I reject H naught, then I can say that I have enough evidence to support the alternative hypothesis, which in this case supports their claim. I can't reject H naught. I failed to reject it. My sample proportion was not statistically significant. So I can't support their claim. Thus, we lack sufficient evidence to support the claim that the rate drop in battery defects can be reasonably explained by the new manufacturing process. Our sample result could be due to sampling variability or chance. So I'm writing my conclusion. Make sure you state what your link between the p-value and the alpha level is, and whether you reject H naught or fail to reject H naught. So that is, look at that. That is a lot. And that is what a hypothesis test looks like. Let's do another one. So on the next page, we've got a new problem. Technology is dramatically changing the way we communicate. A newspaper researcher believes that 65% of households in the US have a Twitter account. In 2015, a random survey of 880 US households showed that 603 of them have a Twitter account. Test the researchers claim that 65% of US households use Twitter. Use a 5% significance level and assume conditions are met. This is like the best thing ever. You don't have to do conditions if it says to assume it's met, but you do need to state it. All right, so first and foremost, we need to define our P. So this is the true proportion, or you can say population proportion of US households that have a Twitter account. All right, now think about what the claim was. The researcher's claim was that 65% of households use Twitter. Is he saying at least 65%, at most 65%, more than, less than? No, he's just saying 65%, period. So that's the null hypothesis. It includes the equality. So P equals 0.65. This supports his claim, because his claim is that 65% have Twitter, which means to go opposite, there was no direction there. It was just, it equals 0.65. So the opposite of that would be not equal to 0.65. Now I said that it was always an inequality. Well, not equals to counts. So with this being a not equals to, this is what we call a two-tailed test. So we're going to look at the math. The math is going to be slightly different, but we've got both directions here. All right, stated to assume conditions were met. So we've got that. I need to name it one prop Z test. Again, write it down. And then I'm going to do my mechanics. So if I have 0.65 here in the middle, and then I need to find my p hat, which it says here 880 showed that, 603 out of 880 households have a Twitter account. So how much is that? 603 divided by 880 is 0.6852. Okay. So I want to go 0.6852 and find this, but I also want to go the other direction, the same amount, whatever that is, and find this way because it's a two-tailed test. So that's what that means. I'm going to find my z-score. I mean, we could write this down. I guess if I do 0.6852 minus 0.65, I get so a difference of 0.0352. So if I take 0.65 and subtract that, it will give me this side. So 0.61477. Or I can just find my z-scores. It might be a little easier to label your curve with z-scores. So 0.6852 minus 0.65 divided by our square root of our p-value, 1 minus p-value over n, 880. And that's going to give me a z-score of approximately 2.18. So I could have also, when I labeled my curve, I could have put a 0 here, z equals 0, and a 2.18 and a negative 2.18. Sometimes it's a little easier to draw the curve with z-scores instead. All right, so now our probability, and now this is a two-tailed test. And our shading, because we're going more extreme, our shadings aren't connected. So we can't write this as one inequality kind of put together. We need to write two separate ones. So we've got a probability that z is greater than 2.18 or z is less than negative 2.18 equals, let's see. So now if I use my sheet, the easiest way to do this is to find this probability first. So the probability that z is less than negative 2.18 is 0.0146. 0.0146 using our z table. Now that means this one is also 0.0146 because they're symmetric. So it has to be. So this is going to be 2 times 0.0146. That two-tailed test means we have to double that probability. So 2 times 0.0146 is going to give me 0.0292. All right, so there's my p-value. Now, our alpha level, again, was 0.05. We need to state it before we talk about it. Now, if you state it in your conclusion statement, that also is fine. So if our p-value is less than or equal to alpha, in this case, 0.0292 is less than or equal to 0.05, then we need to reject H naught. All right, so we rejected H naught. Thus, do we have enough evidence to support the claim? Well, if I'm rejecting H naught, that's what his claim was. I'm rejecting it. So I don't have enough evidence. So I would say, thus we have sufficient evidence to doubt his claim. Or you can say, thus we do not have sufficient evidence to support his claim that 65% of US households have a Twitter account. All right, so the problem is a little smaller when we don't have to write our conditions, but still a lot going on there. This was a good example of a two-tailed test again, so be careful. Sometimes, depending on that claim, if it doesn't have a direction to it, if it's just a solid equals, then we end up with a two-tailed test and we have to double that probability. All right, and that's it for today's lesson.